Hey folks, George Leoniak here. I'm back with another video. I'm excited to be here today. I've got been working pretty hard on some new discoveries that I'm pretty interested in sharing. I've got a overall template and design that I'm calling the Phi Yantra because it's just loaded with Phi ratios. It includes all the Platonic solids and the pyramid dimensions. It's 2D, it can go to 3D. So I've got a bunch of slides in the slideshow. I've got some little forms and things that I've been building and some other woodcut designs based on it. Just been doing some engraving and painting on these, just two different designs of this. It's just a phenomenal form. I've kind of just stumbled into it through all the lines of research that I've been doing. And yeah, I'm really excited to share what the significance of all the lines are in here and how it relates to the small and big picture. So I'm going to be bouncing in and out of the sharing the screen, and let's just get started with that and open that up here. So I've done a little something different today. I've been, normally I do these PowerPoint presentations and put them together, and I have a bunch of slides and images that I can pull on and off. I did all these drawings, or the majority of them that you're going to see, in a highly precise drawing program, just to make sure that all lines are exactly 100% perfect, because we're dealing with Phi here, and I wanted to make sure that these images are just going to be top-notch quality instead of just trying to make it work with some of the PowerPoint. Anyway, that's an aside. It's just the color on these are a little less dull as a little duller, because as they transferred over, they weren't as sharp, but you'll get the picture. So anyway, this is the Phi Yantra, and I'm also calling this the power of the square root of Phi. As you'll see in a little bit, the square root of Phi is fundamental to this design and the relationship between the circles and the squares that we're going to see here. So before, I'm going to kind of walk you through this step by step, and just want to talk a little bit about how I came upon this pattern. Of course, I've realized that, I'm not the first, of course, to discover this pattern. 2 days after I was really working with this, I got a book in the mail, The Geometry of Art and Life by Professor Gayaka, which is just phenomenal. And he's got a huge section on this, which is just great. He doesn't give you a method really in there to show you how to draw this pattern. But this is what got me excited, and I was able to develop the pattern and go from there, and then realize how it fit into these other researchers of this sacred geometry over history have been utilizing. This is how I did it. So, a couple of the numbers here that we're going to be working with is that we've got a 1-inch square in the middle of this design, and that 1-inch line continues all the way out. And, I work with a form a lot called this star cut diagram. And, I really like this form, this pattern and design, because I realized it was a 3-dimensional pattern, which contains this little image that I call the soul star in the middle, which is a little 3D form that fits in there. And, one day I just decided to extend the red lines here beyond the limits of the star cut diagram square. And I realized that they touch where they intersected. That might not line up great for you, but where they intersected they intersect the outer blue circles here, which are part of the design construction to create that square. I was then connecting the dots between the edges of the circle and came up with these two squares in the center around this that are touching the outer edges of the blue circles. And I just decided to then continue those lines all the way through and realize that they met in the corners of what was a much larger square. So I went back and started to, do the math to figure out what the larger square was all about. So this is just, I'm describing my process of discovery of this. And because, you know, I don't think any of the sacred geometry, wisdom, or knowledge that it contains will ever be lost, no matter how many, you know, hopefully never again, books being burnt and temples being destroyed and all that. And hopefully we're in the stage where we're rebuilding all that. But it's all contained in these patterns. We just have to go in and allow them to start speaking to us. And then they start to reveal the mysteries. And a person like me just comes in, starts looking at this, you know, discovers this fundamental pattern just by drawing lines and following connecting the dots here. And, you know, what I discovered is the outer edge of that line, when I continue it all the way through, from one edge to the other and connect to that larger outer square, well, the 1 inch square that I started with meets at the corner here, which then creates a length of 1.618. And of course, 1 divided by 1.618, or 1.618 divided by 1, is the Phi ratio. So I just, through doing that simple design of the star cut diagram, meeting them out here, I've got much more of this on the video. All the 5 Platonic solids are not in the flower of life, which is, you know, really check that one out, because I described this drawing in a little bit more detail. And I wanted to come up with a pattern that contained all the Platonic solids in this view. Which was, you know, more of this square orientation based on the star cut diagram. So, you know, when I add up that whole length of the line, you know, with the 1.618 on either side, I've got this length here, 4.236. Now that's root 5, which of course is the, you know, foundation of the Phi ratio. Root 5 plus 1 divided by 2 will give you 1.618, but this was plus 2, 4.236. So we've got this whole length, and it's divided into these segments going along there. So, you know, the other neat thing here is that what, you know, a couple of years ago, I was really fascinated. See, there's 2 versions of what I call the soul star here. There's the one that fits in this star cut diagram. And then the first one that I actually discovered was this one, which was nestled in this pattern, because I realized, and we'll get to this a little later on, what I realized was that inside the compound of the dodecahedron and icosahedron, I saw that there was another shape within there. And I started to call that the soul star. In fact, one of my earlier videos that I did, where I, because it's very similar to the tetraxis hexahedron, this shape here is the tetraxis hexahedron without the square in it. And, you know, for a while, I thought this shape, the Phi-based one, was the tetraxis hexahedron, but then realized that these 2 shapes are actually different. This one is going to touch the top of the dodecahedron and icosahedron, where this other shape is part of the soul star, which will primarily build you off of a 1.5 length. So this is going to be 1 inch square, 1.5 to 2 inch, and that's going to keep you in that, where this one is built completely on Phi. Now that nestles down right in to fit into that shape right there. And when we show you the Platonic solids later, you'll see how that form fits right in there and how it connects to those other forms. So I just want to show you that, you know, I have another smaller pattern here in the middle that, you know, I did some more connecting of lines, and this Phi Yantra will also go inwards into the center and create smaller and smaller squares as we go in circles that are all in Phi relationship. Just to compare this to the soul star or the star cut diagram, I'll put that over. You can see that that shape is much larger when it's created compared to the one that nestles in there. So they're 2 different ones, but the way that I created this was based off of the star cut diagram, by extending those lines out to connect to these nodes here. And that gave me the template to work off of the basic pattern. So I'm going to kind of walk through this, you know, a little bit step by step to kind of show you the Phi relationships that exist in this pattern here. Oops, didn't want to do that. So as we go through, we're going to have a series of squares that are built off of the these nodal points that we see here around the outside. So this square is going to line up in here. And as you do the math on all those, you'll see that the successive build out of squares starts, you know, from the smallest one, which these are going to be all in Phi relationship as we go out further and further. This is supposed to be 0.38. 38 is in relationship to the 0.23, is in Phi relationship to the 0.38, to the 0.618, 0.168 to the 0.618. The 2.618 is in Phi relationship to 1.618, and the 4.236 is in relationship to the 2.618 as a Phi relationship when these are divided amongst one another. So we just built this successive pattern of squares that are all, you know, nestled Phi harmonies based on this pattern. And, you know, they're basically created by these intersecting nodal points. And I'll zoom in so you could see the closer one of what's going on down in here in the smaller little diagram that I drew in the middle. You'll see that the square here fits around that section. The square here connects at those nodal points. And if this square, of course, fits right in the last little Phi base soul star in the middle. So you have the 1 inch square having kind of 3 layers of squares out of it in Phi relationship, and also 3 layers in Phi relationship. And I'm just drawing boundaries here at this. I mean, I can continue these lines. You'll see in a little bit how the pattern is self-replicating. And, but in this nice little, you know, actually I did this one with the inner and the outer forms. So I nestled these in and did the inner design and then blossomed it out. So I have 7 layers of Phi base squares here. And this is why I'm calling this the Phi Yantra. You know, it's a little bit of a play off of the Sri Yantra. So I figured that the Phi Yantra would be nice to have one of those too. And like I said, it's not something I'm just making up here. The math and the numbers don't lie here. Anybody that starts to draw this pattern is going to come up with these same numerical values if you start with a 1 inch square. I'm not elaborating on the design at all and, you know, getting artistically creative with it other than coloring in the pattern. The pattern itself is universal, let's just say. It's not ever going to change when you draw it this way. It's the only way to draw it this way, really. You know, there's other views, like from the pentagonal faces or vertex view, or from edge view. You know, there's other ways to look at it, but from this view, which is, you know, edge for a dodecahedron, it's a face view for other things like the square. So anyway, it's just a universal pattern is what I'm getting at. So I wanted to touch base on the pyramid because that's going to be an important part of this discovery here, because as you know, well, you know, as I'll describe here in some of my other videos, the Kepler's triangle here, which is what gives us this value here of 1.272, which is the square root of Phi. As you see in just a moment, the square root of Phi is going to be a really important component to this whole design. So you know, if we have a base of 1, or the azimuth of 1 here, if it's 2, if it's the full length of the base of the pyramid, so if it's fully 2 inches, but if it's 1 and we're doing Pythagorean triangle here, 1 and the hypotenuse here is 1.618, well then this edge is the square root of phi, okay, the height. Basically the height of the pyramid is 1.272. Now this is the perfected phi pyramid. Now the actual pyramid in Giza is based on 1.2727272727, and there's a lot of debate about which is the most accurate. It's so close, and what they did there was based it on a 14:11 ratio, and that allowed for the an easy construction based on those numerics. But if we're using these irrational numbers, we can get a little bit more precise here with the actual square root of phi, 1.272. And now I'm able to construct in this view here, all the way from the smallest little pyramid off the little square that's down in here, successive pyramids that are built off of the foundation of these squares. I've cut these squares in half to show you the upper ones. And now we're going to square the circle on all of these pyramids. All right, so from the apex of the pyramid, we're going to draw a circle all the way around, and on the bottom half, it's going to cut through the corner of the square. Now that is now creating a perimeter of the square that is equal to the circumference of this circle, and that's called squaring the circle. So here's our little Kepler's triangle as just one of this. So this is just an amazing drawing because, you know, most times you see this squaring of the circle, you see it as a kind of one-off, you know, square and circle in a pyramid. Well, this is now pyramid and pyramid and pyramid within pyramid, all squaring the circle at multiple scales, all within phi harmonics throughout the whole thing. And it's just, it's really phenomenal. And I didn't realize this till I did this drawing, is that the larger pyramid will actually contain, if this pyramid was also going down, will contain this sphere of the smaller, the next circle down to the next pyramid. So the sphere around this smaller pyramid is contained within this larger pyramid. And I checked this out in the mathematical program to see if those are actually tangent to one another, and I'm not just eyeballing it. And they are tangent to one another with no error that I could be detected by the program, at least. So it's pretty much right on. So we had these nested pyramids within one another, which is just awesome. And now, you know, what is this squaring the circle? Why is it like fascinated geometers? I'm going to get to the other type of squaring the circle that's often referred to. It has to do with the equal areas in just a moment. But this has to do with the perimeter of the square, which represents a matter. And this has to do with the circumference of the circle, which represents the spirit. So if the two of those have these equal perimeters, they don't have equal areas, but they do have equal perimeters, then that is the mystical squaring of the circle. And the matter and spirit coming together with zero difference. Now, you know, a lot of this is, I need to address this portion of this now because it's going to be coming up more frequently as we go on in our discussion, that when you do the, there's two versions of phi. Well, there's one very standard accepted pi, I mean, the pi ratio, pi to get the circumference of a circle, which is 3.141. And this is what you always plug into your calculator. It's programmed into just about everything. And when you do this perimeter, the circumference of the circle, here, which this is the from here to here on this one. This is based on a 2-inch square. This is 1.272, and you multiply it by standard pi, you'll get a circle circumference of 7.999, something like that. And, you know, because pi is considered just transcendental number that will be totally irrational. However, Jain magics, Jain 108, you know, brilliant sacred geometer, artist, number, mathematician, he's really popularized and brought back this ancient knowledge around the true value of pi, which I've used to test out things because I find it to be making all the mathematics much more sense. Because, you know, first of all, to get that, you have to use the square root of phi. Now remember, the square root of phi is this distance of the pyramid. And if you divide that by 4, which is the base of the pyramid, then what you'll get by 2 corners of the pyramid, 2 sides of the pyramid, what you get is the 3.144, and then it goes for maybe 15 digits, and then it repeats that number 3.144 again. Pi, the standard version of pi never has any repeating numbers, but this pi version does. And now if you calculate that, you will get a circumference of a circle that equals 8, and the square perimeter will also equal 8. Now, if you're doing this off of the 1-inch square, you know, everything scales. So then you would have a 4-inch circle with a 4-inch perimeter, and the rest of our drawings are going to primarily be focused on that. But since Kepler's triangle is built off of the 2-inch width here, we are going to just look at it in this instance and talk about this circumference to square as being equal. It's the only way to do it is with that value of pi. And once you do that, all the mathematics of all these pyramids, all these circles, everything makes sense because of that value of pi. And he's got a few different techniques. I'm not going to go over them in this video. He's got some YouTube videos on there to check out how he does that. But it makes a lot of sense because, you know, Archimedes, 2,225 years ago, he gave us our version of pi, which he considered to be as close as he could get. And what he did in doing that was, you know, he created a circle. He divided it into 16 and kept dividing it, you know, by 32, then by 64, by 128, you know, 256, etc. So this little circle continues to get smaller and smaller segments all the way around. And then he's just going to calculate the length of each of those little segments to add it up. And Jain talked about, well, what about that little bit of gap between those lines and the outer edge of the circle? Are we accounting for that? And that might be this little difference here, 3.141 to 3.44 difference of all those little gaps that are added up. Basically, everything comes up to a similar result in the end, but with this version of pi, the Jain pi, then all the mathematics for pi make sense because they're all based on Phi relationship, and there is a pi-Phi relationship. Okay, so that was a lot to cover there, but it's an important thing to start to get into mass consciousness, and I know Jane's working very hard on that too, and I'll continue to be an advocate for that as well. Just as an aside on that is, you know, it just goes to show how entrenched we can get or how attached we can get. I mean, think about our all the systems that we have, all the calculators we've produced, all the inventions and mathematics, discoveries that have been built off of that version of pi, the standard version of pi. What would it take to really, you know, revolutionize this slight adjustment in pi? What does it mean for all the calculators that people have bought and all the different programs that are written on it? You know, that's the type of mass revolution. But could that slight difference in all our technologies and all our buildings and everything that we do create this slight disharmonic that, you know, we just are now thinking we can't change because they're so entrenched? Or is that because we just can't let go and move on with something new? So, you know, it's time for some change and adaptation. So maybe these slight adjustments are totally irrelevant and important to our changing and evolving consciousness. So here is the temple template that I wanted to show you, that you could print this out. It's just a little aside, my new geometers Facebook group. You know, I'm posting some of these little printout templates that people can print up and draw in or color on or cut out themselves. So check out that new geometers Facebook page, because I'm going to add, you know, specific things to that group that I set up. So okay, the temple template. So this is the template that I was just showing you. That's a portion of the Phi Yantra without all the circles and everything. It's got, I scaled this one up to the 2-inch scale. And now this is really awesome, because if you were to just cut out this, you know, orange triangle shape with this square here, and just fold up those edges, this is good, because this is 1.618, and this is now 1.902, this length here, and this is a 2-inch base. You fold up those edges, you tape it together, and there you go. You have your pyramid with the actual height of the pyramid being 1.272. That's all you need, is just this design. You know, if I can just picture, you know, in Egypt, you know, just drawing these lines on a papyrus and just saying, hey, this is the temple design right here. We just fold these up, we build it like this. These are the dimensions we need. Let's just scale to that size, and this is what we get. So that's as simple as it is. And let me just hop out, because I know I've been on here a bit. So this is the design. And, you know, a lot of times, oh, yep, you see, this is how it's built. This goes right there. So this is the pyramid just on the temple design. These fold up, and you can just put that upright like this. So now it's flat, and now the pyramid is flat. And then all you're doing is just folding up these sides with a little slit here and a little slit here. And you've just created, you know, the pyramid with the right height, and the circle that will touch the pyramid and square the circle, square the base of the pyramid. So it's all contained right in this simple little diagram. And this is the moon, relative size of the moon, in relationship to the relative size of the Earth. Very close. It's just slightly off with this more accurate version of pi. It's kind of funny, the 1.27272 version, when you do the mathematics for that, is actually closer to the Earth and Moon dynamics. But if we base it on pi, an Earth-Moon ratio. So here I did it, made it a little more colorful. And same thing, there's the pyramid that sits right there. There's the moons around it. There's this view like this. And, you know, here's a nice little, you know, display of the pyramid with the temple and the template. I posted a few posts on that. Very simple design, and it gives you the perfect the pyramid, just like that. So that's why I feel this design is so relevant and so important to, you know, brings a lot of things together, I guess. That's what it's doing for me. It's unifying a lot of other things. I'm going to bring the Platonic solids in here in a minute, but I have a few more things to cover. But it's very, very much unifying a lot of the, you know, separate areas of sacred geometry. Like you got squaring the circle over here. You've got Platonic solids over here. You've got, you know, the the phi ratio over here. And this kind of brings it all together. So I'm going to talk about the circles now, and the in relationship to the squares. And what we'll have to do here is go to this slide here. And I want to really talk about the power and the beauty, to the power of phi, because maybe this is known to someone else, but I'm a kind of unconventional geometer mathematician. I just make up stuff as I go along and discover things to realize that someone else had discovered that. But I do things in kind of an unorthodox way because I'm not really trained in this other than just my own intuition and inquisitiveness. So I wanted to figure out like what happens between the relationship of these red and blue circles. So all the red circles here were all the circles that were contained within the squares. And these blue circles were all the circles that were the squaring of the circles. That squared the square. The circle that went around the square, to put it into that relationship. So here's the 1-inch circle to the 1.272, and the ratio between the diameter of the sequential red and blue circles is 1.272. So every single ratio between these, 4.236, if you divide 5.388 by 4.236, you should come up with 1.272, and that's the ratio between these two. And then the ratio between the diameter of these circles, all the red ones here, is phi. So of course, this is phi relationship, 1 to 1.618, 1.618 to 2.618 is in phi relationship. Those are all, and then all these blue ones over here are also in phi relationship. 1.272 is in phi relationship to 2.058, as 2.058 is in relationship to 3.330, as it is in relationship to the next number. So as you can see, this is what the wholeness is about. This is what the phi relationship is talking about. It's saying that the lesser, the smaller, is equal to its greater, and the two of those combined is, that is equal to the greater is equal to the whole. So it's this vision of wholeness. It's a description of wholeness based on these numeric. And this, besides just doing it with the straight line, describes it as these spheres or these circles in relationship to one another, also maintaining that harmonious phi relationship that goes, well out beyond the 1.618 that we're used to, but they maintain that relationship. And when we put those two together, meaning, when these red circles fill in the gaps between the blue ones, well, then their relationship is the square root of phi. And then I just happened to discover that, what happens if I just take the square root of phi and I just raise it to the power of, right? So I've got 1, okay, that's 1. I got phi. Well, I'll raise square root of phi, of course. Well, if I square it, it's 1.618. I just put the square root of phi squared. We already know that's 1.618. But here's it gets interesting, because now let's raise the square root of phi to the third power, right? Well, that gives us 2.058. Okay, let's raise it to the fourth. Okay, 2.618, raise it to the fifth. That's the 3.3 to the sixth, 4.236, raise the square root of phi to the seventh, the 5.3. This will continue on forever, creating that relationship of the phi relationship between the square and the diameter of this circle, which squared the circle, in relationship to this circle, which was inside the square. Hope you all caught that. It's just really amazing for me to discover that all I have to do is take the square root of phi and raise it to the power, and it will continue to produce these harmonic ratios. So here's the neat thing that happens here. All the ones that were in the squares are all raised by even number, 2, 4, 6. Of course, the next one will be 8. And then these were all raised by 3, 5, and 7. So we've got the even numbers on one side, the odd ones on the other. You know, just little discoveries like that, I think have some really important significance beyond what I can understand how it does. Maybe someone else will take it and go with it. But I continued on with this train of thinking around this. And so I was working, here they are all together. And then the ratio of the area. So I wanted to start looking at the area of these circles, these sequential circles here. So the ratio between the area of these sequential circles, the red and blue circles, is phi, all right? So in this one, and I might have confused that here, this was about the diameter of the circles. So, you know, this is, I'm talking about the diameter of these are increasing in phi, the diameter of these are increasing by phi. Then I wanted to look at the area of the circles. And I started off with the area of a 1-inch circle here. And then that is in relationship to the area of the phi circle here, the square root of phi, which is amazing that the square root of phi, the diameter of the square root of phi, has the same area as the square root of phi. It might be the only form, the only geometric shape, the only geometric circle that has the same diameter to area is the square root of phi. Granted, we're using all this Jain pi 3.144 to do these calculations. It will be slightly off if you use standard pi. This is what I mean, that all these harmonics of all these phi-based mathematics are all done with the Jain pi, the true value of pi, to make sure that all these numerics remain and retain their phi-based relationship throughout all of these. So the area between this and this is phi, the area between this and this is phi, the area between 3.333 to 2.058 is phi. And the awesome thing about the area of these circles as you expand out is that they're all based on squaring the you know, they're skipping the number here, the 3, 5, 7. So it's all the odd numbers or areas here that are all increased by the phi. All right. And over here, the circle diameters, as I've mentioned previously here, these are meant to be paired together here. So anyway, just this is all contained now, once again, in that Phi Yantra diagram we just showed to you again at the beginning. This simple design, these little orange pyramids, that's the pyramid, that's the blue circle. This is the red circle within the square, the blue circle to the pyramid, red circle in the square, blue circle, red circle, blue circle, red circle, nestled in squares. It's all contained within the simple diagram of drawing these lines that I showed you here. Contains all these root harmonics. So we've talked about the circles. There's one more the little discovery here that I'll put in here as well. And now I've talked about the perimeter of the circle and the area of the circles. So those are the area of the circles in relationship to one another. But what about the area of the square to the area of the circle? So this is not to the 1-inch scale here, these drawings, but I made them larger because it was just too small. So this is now based on a larger number that's still maintaining the Phi relationship. But just pretend it's 1 inch. So this is a 1-inch square. So, you know, 1-inch edge all the way around. So it's got an area of 1. So, you know, just playing around with the numbers, I decided to go, well, what's the square root of the square root of phi? So it's a square root of the square root of phi. So it's a square root of 1.272. Well, that's 1.127. And 1.127 just happens to be, when you calculate the area of this circle here, you have to take the radius of 1.127. So you divide that in half and you get 0.563, and you've got to square that, okay? And then you're going to multiply it by the Jain pi. And when you do that calculation, the area of that circle is 1. And amazingly, it's based on the square root of phi. The number that it's based on is the square root of phi, the square root of the square root of phi, okay? So it's double square root of phi. And when you use Jain pi, you get that the area of the square is 1, the area of the circle is 1. If you do standard pi, the area of, here's the standard pi, 3.141, then what you get is, with the same radius, you get 0.999. So you're off by that 1 digit there. That is, and it's further on down there, then all the numbers continue to be different after that. But it's so close, yet why do I want this? So when I could just go with everything based on the square root of phi. And so the beauty of that, what I'm saying here, is that the square root of phi, 1.272, to get the equal areas, all you have to do is just square the square root of phi, and then you automatically come up with the diameter of the circle that you need for that radius to get the area of the circle. So, here's all three together. You got the inner circle based on the 1 inch square. There's the area of the inner circle. There's the red circle here corresponding to this. That's the square root of the square root of phi, the 1.127. And then, of course, here's the one. So this is the one that gives you equal perimeters, is the furthest one, which is the pyramid is based on, is the 1.272. And that's the diameter of the larger circle here, giving you equal perimeters. Like I said before, just need to realize that, when I do the calculations, that the square root of phi, the diameter of that circle, has an area of the square root of phi. And I just thought that was phenomenal. That's, of course, when you're using the Jain pi. So, okay, that concludes this kind of first segment. Besides that, it's a very neat little optical illusion here. Really, the three of those circles together, when I look at the center of that, kind of really warps the outside of that square for me. Reality warping. So, all right, cool. So now we're on to the next section of the Platonic solids. So, like I said, all of the Platonic solids are contained within that same root design. And I've just arranged them here like this and this is a bit of a discovery in the making of this presentation. I just said, well, I'll put a few of these Platonic solids all on the same page, and I put two together and I said, whoa, wait a second, I'm starting to reproduce a pattern here that looks familiar. So then I popped the other two in over here, and now I've just reproduced that giant soul star, the phi-based soul star in the middle, another version of it here, and I've created another square, and I'm going to reproduce the whole system again. So just a really neat, discovery just in creating this of how these nestle together. But here are the first three Platonic solids. I put the two tetrahedrons here because there are two tetrahedron in the Platonic, in the nesting of the Platonic solids, because in each square there's two tetrahedron. Now we're not used to looking at tetrahedron like that because this is the edge that's right on edge view towards you. So you're only seeing two of the sides, where this dotted line is showing you that the other two sides are behind it. This octahedron here, of course, fits right within the cube. Its points touch those. this edge here of the tetrahedron will be the edge across. This is now, if it's a 1 inch square, so that's √2 going across, making the x, 1.414 going across this edge. So we got √2 in there. And, you know, so I made all these little Platonic solids to sail. Once I get through these a little bit more, I'll show you some of those. And, you know, I just want to go into the dodecahedron. So we can take a look at the dodecahedron. So now this is really where I got started with a lot of these discoveries here, was before I even realized that you can extend those points out to the larger square. I was just drawing the dodecahedron and icosahedron in here. I'll show you that one in a minute. And, you know, looking at this shape, because it's easily contained within these lines, it fits right within, and it's just bisecting that little section there to come up to create the furthest edge. So this has got an exact dimension of 0.618. Each of these edges will have 0.618. You can do now every dodecahedron is made up of 5 cubes. You know, normally we'll see it just with the square in the middle, like this, which is the square that faces you dead on, and it's a flat face. But once you put in the stars within each of the dodecahedrons, each of those edges is actually a portion of another cube that's in there. And very cool that this pattern here, we can just isolate and pull out one of those squares in here and show what it looks like from that view. So, you know, I really like this because, you know, instead of just having the square, which gives you the √2 value, the other important value that is in the square, in the cube, is the internal diagonal from one vertice to the next across the inner length. And that's 1.723 or 1.732, the value for √3. Getting the 2 and the 3 mixed up here. Let me just double check for everyone. And 3, 2, yeah, it is 3.2. 1.732, so the value of √3. And that will be also the internal length, because remember, there's a cube in that dodecahedron, which I'm showing you here, that also has a vertice down here and a vertice here. So you have 2 versions of the cube in there. One's giving you the √2 value, and the other one is giving you the √3 value. Both of those are, you know, when you draw the Vesica Pisces, both of those are in that Vesica Pisces, or at least √3 shows up in Vesica Pisces when it's a perfect Vesica Pisces based on 2 circles of 2 inch diameter. You'll get √3. So this, you know, Phi Yantra is, you know, giving you both those dimensions in here. And the other cool thing about this is this is probably the only angle that you can view the cube at to have these edges segment these lines by the phi ratio. So from here to here is in phi ratio from here to here. And same thing along here, from here to here is in phi ratio to here. If you measure from here to here, and this bent angle from here to here, that's in Phi relationship, these 2 angles. I just want to let you know, when I do this mathematics for this, you know, I have some Phi calipers. You know, I look at them and just be like, oh, that looks close. But then I go in and I do all the calculations to make sure, with the right angles and making sure all the decimal points will be within the pattern. So when you are dividing things, things are working out, you know, accurately. So, you know, I test out all these measurements, and I have them all written down somewhere for what every single one of these little phi-based segments are. doing the mathematics and using the right triangles. And it's a real mystery to discover where the right triangle is and then figure out those dimensions. But it's very enriching for me, and it just really allows for this to stand for itself on its own without the eye, which really can be misleading. Saying, oh, hey, that looks close, that must be phi. It's been off plenty of times in my geometry career here, and now the mathematics don't lie, as long as you're doing them correctly, which I hope I am a lot of the times. So, like I said, that's probably one of the only versions of the cube that you can look at it, where these dividing lines are cutting the segments. So it's like a spiritualized view of the cube. But the cube, a lot of this is built off the 1-inch cube, and now we can build the icosahedrons off of this. This icosahedron here, both of these, this internal view here, these are creating golden rectangles. You draw this line through that segment, parallel line up to there. Well, that will give you this 1.618 edge length, which means all these edges here have 1.618 edge length. And here's another golden rectangle in the middle. So we know if this is 1.618, well, if it's in Phi relationship, this one will be the square root of phi. I mean, not the square root of phi, the phi squared, which will be 2.618. And so now we have golden rectangles within there. It just so happens that, when you do that same thing over here, you can do it easily with the 1-inch edge, and that will fit in a 1-inch edge there. And there's your two versions of the icosahedron. Later on, I'll show you can create the icosahedron that fits, within the whole square easily too. So this is there's a lot of information in this. If you're really into this, I watched this a few times because you might want to try these calculations to test out the things that I'm talking about with the math, and also, draw some of this, study some of this. I find it to be, this is a really expansive, consciousness expanding design, because we're bringing a lot of elements together here. So here's we're going to do a couple more forms here that are not the Platonic solids, but we get to them through the Platonic solids, and they have phi-based relationships as well. What we have here is the compound. The dodecahedron and the icosahedron are dual forms. So the edges will overlap bisect each other, or one will fit inside the other. Here, the edges are the bisecting, and when you have that, which are the two versions I showed you before, then what you can do is create the rhombic triacontahedron, which is a 30-faced shape, which has 60 vertices around it. And it's these little cross sections are the contributing factors, contributing pieces that come from the icosahedron, which is the blue, down the center, which is 1 inch, and the 0.618 here, which is the red one. Those two contribute together from the dodecahedron and the icosahedron, and that gives you a rhombic face, which is in Phi relationship to one another. The height to the width is a phi. So rhombic triacontahedron is, kind of our next level of consciousness expansion from these forms. A lot of it people consider this is the Earth grid that goes around the Earth. A lot of the sacred sites, the vertices line up to specific locations on our planet. So definitely a sacred form that's based on Phi and the relationship of the icosahedron and the dodecahedron. Another form, because the rhombic triacontahedron also has a dual form, and it's called the icosiedodecahedron. Here I'm going to show it because it's very easy to draw within this Phi Yantra pattern that I'm showing you. it's basically within the pentagonal faces of the dodecahedron. It's another pentagonal face connecting the internal center points of the first dodecahedron. And that will create these 20 triangular faces and another set of 12 pentagonal faces. And that form, of course, like I said, it's 30 vertices it has. They'll meet when it's inside that rhombic triacontahedron. They'll touch those central points that are in each of those rhombic faces. So you have that combination of those two there. So let me just stop the share one more time and just show you some of these little miniature models that I've been working with. First, let me show you this. So, like I said, this is one of the earlier little template designs, same design that I also folded up. You see that those outer edges go over to there. This is based on a few golden rectangles here. And then these darker lines within here, are basically, this is the Great Pyramid, right? Here's the Great Pyramid, the mini Great Pyramid, right? There it is. It sits right on top. There it is from the side. And, this inside here, is containing also the blueprint for the rhombic triacontahedron. See, it's in the template. It's right in there. It's also in the icosahedron is in there too, just like I was showing you. So that's the icosahedron template. The dodecahedron is also within this blueprint that we're looking at. The tetrahedron, like I was showing you before, with just a line, that's just one of the edges that's in there. The square, of course, that's the 1-inch square that we've been basing this all on, right there, the cube, I mean, and the little octahedron right at the center of it all there. Now that octahedron has a point that's coming towards you. And then, when I did this one, originally I dropped the little, there's the little soul star, the mini one, that's not the Phi one, but it's the other one. That one fits right inside, and that's based on the star cut diagram. So I did all these little forms, to scale as well. So here's the little 1-inch cube. It sits right in there. These aren't going to fold up like that, maybe if you sink it down in there. It's, containing the template. This is the little, the octahedron, and each of these points will touch where these crossing lines are. So we got 6, so this is the dual of this one. The tetrahedron, is, the cross faces of the cube. So this diagonal line that would go across here is the tetrahedron. And the way I'm showing you it in the video, or in these slides here, is with the edge view like this. So, it looks like it could be a cube. It's hard to tell that those are slanting away from you, going back to where I'm holding it. But, it's just a triangular shape because there's 2 of them in there, right? And I did a little mini one because the octahedron that's in the middle, if you build the little triangular faces off of that, these little tetrahedrons, so it's got 8 little tetrahedrons that go off there, well, that's going to make, because at the center of each tetrahedron is an octahedron. So those 2 octahedrons meet in the middle. They share each other's place, and the remaining bits of the 2 tetrahedrons extend out beyond that. So, we're looking at the tetrahedron like that, the star tetrahedron. A lot of people like to view it like, on the vertice like this. So that's the other one of those. The icosahedron and the dodecahedron, the 20 faces and 12 faces. This one has the large pentagonal face. This one, of course, has the smaller pentagonal faces. These two are the duals. When these two join together, will create the compound that is this little rhombic triacontahedron, which has got that 1 to 0.618 rhombic faces, the 30 rhombic faces. And this one is the one that will, be part of the design template. The lighting is a little poor, but it, fits into this model. So, what I'm basically saying is, you don't really fold up the pyramid around these unless they're in there halfway. But it's a design that shows you all the drawings in there, including all the other dynamics that I've been showing you. This is the soul star, and this is the other version of the soul star, the phi-based soul star, that I continued off to create the cube around. The height of those two are different, but these two are two important forms that I think need a little more attention. This one is the tetraxic hexahedron, which does exist, but this one here, the phi-based one, the other soul star that I am talking about, is another one that is also an important link in the forms. Okay, let me just wrap things up and get almost done. I'll share the screen. And so here I decided to, when I joined those four together, when I was showing you the first tetrahedron, octahedron cube, I decided to scale everything up and now place a larger template over top of the small one. So here's the four, and then I took the large icosahedron and placed it over that. And these edges here will meet right up to the corners here, another larger golden rectangle. So this is, twice the size, 4 times the size as one of these. And now we've made this another larger one. And what happens when you do that is that everything scales up to the next level. Instead of it being the 1-inch square, which was here at the center, well, now everything's based on the 2-inch square. And now we are into Kepler's triangle. So when I fold up these edges of this triangle here to create the pyramid, I will create a Kepler's triangle with that, because now the distances are going to maintain the ratio of a 2-inch base rather than a 1-inch base. So it's really the ratios between these things rather than the actual lengths. The lengths can change, but the ratio and the scale between them remains consistent. So when I did this, of course, here is this length from here to here is 5 plus 1. That should ring a bell, because 5 plus 1 is part of the formula of phi. So 5 plus 1 equals 3.236, right? And then, plus 2 is 5.236. But here's, if we divide this, which is how we get phi, root 5 plus 1 divided by 2 is 1.618. So here is an edge length to the 2-inch length based on this Phi Yantra that gives you the measurement, or the most used way to get the phi ratio. Square root of 5 plus 1, divide by 2. Okay, so here's the Phi Yantra. I enlarged it to the 2-inch version over top of the 1-inch versions, and it fits beautifully over top. The multiplicity of new lines that have entered into the larger lines all overlay that large square, that the corners of the two tetrahedrons, octahedron and cube, they now fit within the pattern here. They just get engulfed within the other large square as the Phi Yantra builds out. And now you have a bunch more harmonic relationships within Phi. I believe this is an ultimate universal creative pattern here that should be introduced to every young person on the planet to understand mathematics, relationships, and geometry. Any young or old person, anybody in this process of awakening and relearning and awakening and remembering who they are, where they came from, what's the relationship to creation. No one has to tell them these things. Just start exploring this stuff and allow the mysteries to present themselves to you. And everybody can take this even further than I have, especially the younger people out there who are going to get this instantly and take it to new heights. But it does come from an ancient blueprint. I mean, the pyramid, some people say 5 to 10,000 years old, maybe even older, contains all this just phenomenally, or at least near close enough approximation of it to get us pointed in the right direction. But it's not only showing up there. As I got really excited about this design that I was working with, before I really knew anybody else created it or was working with it, this usually happens for me. It's like I have to, I discover something only to realize someone else was working with it. I do believe the construction method that I show you early on in slide 2 is a novel approach. I'm sure it was used before, but I haven't seen that utilized before, because this book by Gayaka, The Geometry of Art and Life, is actually a free PDF online I found today. I just pulled these images from there to show you how what we've been talking about fits over the Pantheon, because the Pantheon in Rome, he has a picture of this in the book, and he talks about this 1-inch cube at the middle with the radiating out, creating the larger square around the outside, which squares the circle. So this morning I said, well, let's just lay over what I've done just right on top of this Pantheon, which is like just such beautiful architecture that contains the blueprint of cosmos. It's up there with the pyramid and its type of architecture. And it's not only one of many, many places, but it's got this Phi relationships built into this root design that I'm showing you here, was encoded right into this. Here's the 1-inch square. Of course, I've gone further in with this design and added, a few more squares to continue on. Notice this square will meet here, but the ones we really want to, let me back out just a little bit. The ones we want to focus on, I couldn't get this lined up and tilted just right. But, this squares the circle, because here's the larger square. And here's the diameter of the circle that is squaring the largest outer square that the Pantheon is built on. And it's built off of the 1-inch square in here that, if you continue these lines back to here, meet these little bulbous areas out here that come out to the sides. These little sections here are fitting within these squares. And this line here is divided into the Phi ratio. So here, if this is 1, this is 1.618 over here. So, this is what I said earlier, like, we can construct and build beautiful architecture. I'm sure many architects who are aware of this. All I know is that I stumbled upon this template and blueprint just kind of out of thin air, and my own intuition and research and discoveries that come to me through just asking questions, drawing, contemplating, building stuff, building forms. You become in your own relationship and connection to this, and it will teach you everything you need to know about how it's all connected. Not perfect, but good enough for me. In Gayaka's book, he shows a couple more things that connect a few other links together for me based on the same design that I'm glad we're in there, because I hadn't gotten there quite yet. I'm always looking at how the Phi relationship, or Da Vinci's Vitruvian Man, how do Phi proportions work out? How did he draw that? In there, he shows 2 pictures, one of not the Vitruvian Man, but another scaled human in here. So I did my own design of that, and it's, you know, the same 1-inch square in the middle, the 1.618 divided with the larger icosahedron, showing where the heart is, the length of the arms, the width of the head, the outer angles of the feet, you know, the center point. The navel is just a little higher than the center of Da Vinci's navel, but even on his drawing in the book, it's a little higher where that line goes across. He also has this beautiful woman, which this is not one of them. This is me here with her head, you know, showing better Phi proportions than I have here, but you know, you put this icosahedron on your head, which of course is the same design, and you see where the eyes line up and the forehead and between the eyes and the tip of the nose and the center of the lips to the bottom of the chin. Had a hard time finding where my chin was though. But anyway, you know, it's good enough. It was good enough for me. It just tied together how this all applies to, you know, really, I guess the kind of take home message with all this, and where sacred geometry and where this Phi Yantra is kind of bringing us in connection, and sacred geometry in general. To see those last two slides about the pyramid and the Pantheon, you know, these things that are representing universal cosmic order, from very minutiae to the largest, in connection with, you know, God, the creator, the universe, how it's all holistic and divine, and how these places are temples. And then when we apply those same proportions, the same principles, the same construction template, which is this template that I'm talking about here, is Phi Yantra, at least one of them, and this is, I think, a really important one, that we overlay on our own body, we see that we are that temple too. And that is the biggest takeaway message, is that we are divinity, we are the temple, we are the sacred geometry. We're the most profound sacred geometry that exists. You know, we have all inside of us, and because we're it. And these things that we create in those same ways help us remember, either through the drawings or through the contemplation of these forms. It helps us remember that we're a temple. We surround ourselves with the sacred objects, understand the significance, harmonize with those, and we're unifying that matter and the spirit, or zero difference. So yeah, much love, peace. I'm really thankful I got to share that with you. I hope you enjoyed what you heard here. And remember, New Geometers is a Facebook group where I'm going to be sharing a little more information on these things. I've got my blog at newgeometers.space, which I'm going to be right up on this soon. And at that New Geometers Facebook group, I'll share some of these templates that I'm putting out absolutely for free, because I believe that everybody deserves to have connection and relationship to this content and material, to help with their process of discovery. Okay, so yeah, thanks for watching, and I'll talk to you next time. Looking forward to the next videos. All right, peace.